Okay, so those who were missing in the previous classes, I hope you have revised the content. Fine. Is that all right?
Yes, sir.
Good. Okay, so welcome to fifth lecture of Advanced Electric Drives, and we have discussed a lot of things related to the mechanical systems, stability, instability, and how to understand that. Now we have slowly moved towards the electrical subsystem, and particularly we are looking for the realization of DC-DC power electronic converter. So first question what we asked ourselves, that why do we need power converter, or what do we understand by power electronic converter? So we have seen that it is some kind of interface which is coming between the source and the load, so that the desired voltage can be applied at the load end irrespective of what is the source voltage or frequency, these kind of things which are available with us. Now in case of DC-DC voltage, let's say the input is DC voltage of 10 volts and load needs 5 volts of DC voltage, we see that even a resistance could do that job. So equal amount of resistance can be inserted in between, and this can drop the rest of the 5 volts, and then this could be fine. But the problem comes with voltage regulation and the efficiency. So to overcome that, at least one issue of voltage regulation, we can have variable resistor, which can be realized through some power BJT acting in the linear zone. So these things are there, but the power loss still remains the concern, and that is why we see the linear power supplies which utilize this concept for giving a constant voltage output. They are very big in size because so much of power loss they have to accommodate, and that's why the device is mounted on a very big heat sink. So we want to do something better than that, and that is where we come up with the idea where the power can be equated to zero for the system, for the power loss for the system can be equated to zero, and this is true for these two extreme conditions. So then we see that this can be realized by using a single pole double throw switch where P is the pole terminal and we have two throws T1 and T2. And now if we have to apply the voltage at this load, what we see that if P is connected to T1, we don't have any resistance over here, and so we are applying the full voltage at the pole end or at the load end. Whereas when we are connecting to PT2, we have applied zero voltage and the resistance goes to infinity. So ideally speaking, the power loss is going to zero. So this kind of voltage what we have generated from our SPDT switch could be okay for our RL load and even for DC motors. So because they have some kind of reactance coming on the way before the EMF. So this is fine. Now we have seen some of the properties. Let's say if we apply to the resistive load, this is the kind of output current we are going to get over here. So the peak to peak ripple, what is coming on the current and output voltage is pretty high. So the voltage profile is very bad if we talk about the quality of the output voltage. So this we need to improve. So one straightforward thing what can be done is that you connect an inductor in between the load and the pole. So what that will do basically, that will smoothen the output current. So if this is your inductor current, then this is what is flowing in the load as well, and your load voltage could look like this green waveform. So we have kind of smoothened this, and if we further want to improve, so this can be called as some primitive buck-to-buck converter. This is not a very bad design if you want to use it for any circuit, even for capacitive load or anything, this can work well. However, we want to improve the output voltage and current profile, so we can insert another element over here which is basically voltage stiff. So what this will do, it will provide nearly constant voltage at the load end. So basically absorbing all the current ripple flowing into it. So capacitor by nature will provide a short circuit for all the high ripple or high frequency components, and it will seem like a very big impedance for DC current. So naturally we will have only DC current flowing into the load, and so the voltage across the load will also look very much stable. Then we have tried to come up with the waveforms for this converter, and what we see that two possible configurations are there. When the PT1 is connected, this is called on duration, and when PT2 is connected, this is called off duration. And we have tried to make the inductor voltage what is getting applied across this inductor. So when it is on, this is basically Vg minus V naught, and other case it is minus V naught in case of T off. Now, when we want to have steady state operation, what we basically require that if the inductor current is starting at any point, let's say at I min, at the end of the switching cycle, it must come back at the same point I min. If it is not coming, then eventually either the current will go very high or it will drop down to zero. So either of the conditions are not good. So what we must do that we must make sure that this current is starting and ending at the same point, which means if we see from the inductor current equation, the average current inserted due to this component should be zero. Then only the I min can come back to I min. So which is what we have seen over here, the average inductor current going to zero, and this is what we also know as the volt second balance or flux balance. So whatever flux we are injecting during the on time, during the off time we are taking it back. So the current is maintained at the same level. This is the first condition which we must ensure. And then under that condition, if we are operating the converter, this is how the inductor voltage current will look like. And apart from the DC component which is flowing into the load mostly, this ripple component will flow into the capacitor. So based on this ripple component, we can get the capacitor waveform. So you have to note that how it is changing. So during the positive IC, the capacitor voltage will charge from the most negative to most positive. And during this negative current, it will come back to the point, most negative point. So again, we are ensuring that there is some kind of charge balance or ampere second balance for the capacitor. So this is what we have seen. Now, because we say that the buck converter, whatever we have realized over here, does not dissipate any power. So which means what, the efficiency is nearly 100%. So whatever power is flowing into the system is going out to the load. So then we have very clear-cut relationship between the input voltage current and output voltage current. And then what we see that if our voltage input and output voltages are related through this, and that is what we are getting from our this volt second balance. So that is what we have seen in our previous classes also. So this volt second balance is basically giving us this kind of equation, this kind of relationship between the voltages. So if you apply over here in this power equation, you find that the input and output current are related like this. And for the value when D is changing between 0 and 1, which is the duty ratio basically, what we see that the commonly known voltage buck converter is basically a current boost converter. So our output current is more than input current. And obviously because power has to remain same. So up to this the concepts are clear, right?
Yes, sir.
Any doubts over here?
Sir,
Yes.
sir, the inductive current that we draw in the last class is actually of exponential type. But is it true, sir?
Okay, good question. So always, okay, just going little bit away from the power electronic and any system. Let's say we have this kind of circuit. Okay, RL circuit is there. Now this is the voltage applied to it. If I ask you to draw the current, it will eventually become like this, right? Correct?
Yes, sir.
The exponential part, what you see, and it is settling down to some constant value, which is basically V by R. This time period or this time interval basically depends on what is the time constant of the system, L by R. Okay. Now, if we talk about a very large time constant, which means our operating time is very small compared to the time constant of the system, the rise in current may look very linear. Understand the point?
Yes, sir.
And if we talk about the time constant, which is very comparable to our operating, let's say this is our operating time, so big. So it is comparable to the time constant. Then you will see exponential kind of current going and settling somewhere. Correct?
Yes, sir.
So that's the difference when we can have the linear way of drawing the current and then when we can have the exponential way of drawing the current. This is one. The second reason is that we are having constant voltages applied across the inductor. The resistance value for an inductor what we connect in the circuit is very small. So eventually what we see is basically a voltage applied across an inductor. This is always going to be linear. V by L times of T. This is the current. If you start from the beginning. So these are two reasons why we have this linear kind of current for the inductor. Fine.
Yes, sir. Clear, sir.
So little bit more understanding you need to develop yourself. So do some exercises related to this, some circuit analysis, and you will realize that what we are doing. Now, so far we have seen the power flow from the voltage source to current source. That is what we have seen in the buck converter case. We have a voltage source and then SPDT switch is connected, and here we have inductor and capacitor which is eventually forming a current source. That is what this is. Now what we are trying to do, if we can have this way of power flow from voltage source to current source, can we not have the reverse power flow? Yes, of course we can have, because the power source could be either current source or voltage source. So if we are able to achieve power flow from voltage source to current source, in case of bidirectional power flow, we may have current source to voltage source power flow. Correct? But because we are habitual of seeing this as no more what to say, left to right side of power flow, so we can draw this in this manner. We have a current source and a voltage source connected on the load side. So this is the typical configuration which we may have for power flow from current source to voltage source. Now please understand, current source cannot be opened in any condition. Under any condition, you cannot have current source in open circuit mode. So always the current source is going to remain connected with the pole of this switch, T1, T2. Am I clear? Even if it is buck converter or boost converter, whatever, the current source is always connected to the pole. That is never going to change, because we must ensure that current source is never open circuited. Fine. Now with this, let us go to our next circuit, which is basically, so the way we realize our current source is we have a voltage source connected with a current step element. Okay, so first let us see the ideal waveforms for this and how to derive the expressions. Let me draw this current source as it is, and we have say a voltage stiff element, say capacitor, and some load connected over here. Correct? Now when I say current source, definitely it will have some current value associated with this. So let me call it Ig. And what it is doing, basically it is injecting some current I naught into the load side. Correct? Is that correct or not?
Yes, sir.
Hmm? Now if I ask you to draw this I naught with respect to time, so what we are doing, we are connecting PT1 and PT2 one by one. So when we connect PT1, what will happen? The current flowing into the load will be 0. Is that correct? And when we connect PT2, there will be Ig amount of current flowing into the load. And again, the cycle repeats. So I call it PT1 connection and this as PT2. Again PT1, again PT2. Let's say our conventional way of writing is T on T off like this. You understand this point? Because we are dealing with current source, we need to think from the current point of view. What is happening? This is what the quantity we have. We do not know anything about the load, voltage. Correct? Now, on an average basis, what is the current injected into the load? So if you call this as dTs and this as 1 minus dTs, what is the load, average load current flowing into this part of circuit?
Sir, 1 minus d ig.
1 minus d into ig.
You get this point?
Yes, sir.
Now we know that this part of our converter is basically having 100% efficiency, is not having any power loss. So whatever power is flowing from this side to this side is going to remain balanced. The P input is always going to be equal to P output. Correct? So what we will have basically, if Vg is at the input end, the voltage at the input end, and Ig is the current what we are seeing, this is going to be equal to this VO, which is the output voltage, IO, which is the output current. And so what we will have using this expression, that VO basically will be equal to Vg by 1 minus D. You understand my point?
Yes, sir.
Yes,
Yes,
sir.
sir.
This is what we call as the famous boost converter. Voltage is getting boosted because 1 minus D is always going to be between 0 and 1. So this is less than 1. So always we are going to have some higher voltage on the output side. Why? Because it is operated as current buck converter. There is no extra power source, there is no extra energy that is coming from anywhere. It is simple power balance what we are dealing with. This is what we are dealing with, and this is true always. Whether the converter is operating in conduction mode or discontinuous conduction mode or any other thing. You understand my point? And I have not used any kind of voltage balance or anything anywhere. Volt second balance or anything I have not said. Simple power balance equation I am using. You understand this point?
Yes, sir.
Clear to everyone?
Yes, sir.
Yes, sir.
Good.
Yes, sir.
Now let us go to little more practical version of this boost converter. So we will have, of course, a voltage stiff element or voltage source which is connected to current stiff element. This is more practical realization of the current source. And what we have when we draw it like this is our boost converter, which we know little bit, because still I have not said what we are going to connect between PT1 and PT2. How are we going to realize? Correct? At least the rest of the circuit you are familiar with. Now, if we have to draw, let's say the current and voltage waveforms for this kind of circuit, for the capacitor or output voltage and all these things, we can utilize the similar concepts what we have learned for the buck converter. First, if we have to draw the inductor voltage, because that is what dictates how the inductor current is going to behave. So when we are operating PT1, what is the inductor voltage?
VG.
Vg.
Vg. Correct? And when we are operating PT2, what is the inductor voltage? Let's say this point is VO on an average.
VG minus VG.
So I draw it negative. Correct?
Yes, sir.
because of course VO is going to be more than VG, and this cycle repeats. There is no doubt about it, right? So this is our operation which is happening over here. Now what will happen when we connect it across this PT1 is connected? We are having a positive voltage across the inductor. So current is going to rise in this interval. And then it is going to fall back because of this negative voltage applied to the same value. The value of the current is not going to change. You understand the point? And then the cycle continues. Correct? Now if I ask you, what is this IO flowing into the system? What is the IO? Because that will decide the capacitor voltage, load voltage, and everything. So when PT1 is connected, what is the load current flowing? This IO, when I'm saying this includes everything.
0.
Zero.
So for PT1 time, this is 0. Because this is shorted here, there is no current injected in this duration. And during PT2, what we have? The same current, whatever is there in the inductor, that will flow in this load side. And then it is 0, and then it is this. Do you see this? So our load current is kind of discontinuous over here. Why? Because we have current stiff element on the other side, which is maintaining continuous current. But here we have voltage stiff element. So current can be discontinuous, but voltage cannot be. Now this is our IO. Now if I ask you, what is this load current? So during this interval, there is no current coming from the source side. So who will supply the load current during this interval?
Capacitor.
Capacitor, correct. So if you have to draw the capacitor current, what will happen? If this is IC, during this interval, let's say our voltage is, output voltage is nearly constant and there is resistance on the load side. So what will happen? The capacitor current will be a negative value, which is minus V naught by R, or V naught by R negative value. Okay, because that is going out of the capacitor. Correct? And this, when the PT2 is connected, what will happen? Whatever load current is flowing, that will keep flowing V naught by R. But the remaining portion of this current will flow into the capacitor. You understand the point? So how that will go? This, whatever current you have, the average value of only this part, you subtract V naught by R from that, and then the remaining will be your capacitor current. You understanding my point?
Yes, sir.
Whatever this total current IO I have drawn that is coming from this side, still this will keep supplying this V naught by R current, but the remaining portion will enter into the capacitor during this PT2. And that is how the capacitor current will keep flowing. Again, you see that this is kind of discontinuous. And there is no problem because the capacitor is voltage stiff element. So no problem in having a discontinuous current. Understanding my point? Any confusion in this?
Sir, average current is of full cycle that we take.
No, this V naught by R is basically dependent on what load is taking. And this average, when I am saying this is average of only this half, that is what is the current flowing into this load. So from this average only subtract this V naught by R, and then remaining is basically flowing into the capacitor.
Yes.
Now, the capacitor voltage, if you see, during this discharge cycle, if I mark this area, during this the voltage will reduce. Why? Because there is current flowing out from the capacitor. And during this time, when the current is positive, this will basically charge because some current is flowing into the capacitor. So, we will have capacitor voltage going negative during this PT1 or going discharging, not negative. So if I draw the capacitor voltage, not the ripple voltage, okay, please mind that. So there is some average value for the voltage capacitor. This is V naught basically, this value. Now on top of this there is ripple sitting, what is coming because of this current change on the capacitor. So if let us say this is the average value, during this time it is discharging. So let us say from some very maximum value it is coming down to the least value, say over here. And because this is constant current, so there will be linear discharge in the voltage. So VC is basically correct. So from some initial value, say V naught, it will discharge because this current is negative, and it will come down to some minimum value. Now, during this we have linear shape of current. So the voltage for the capacitor is going to be parabolic but with changing slope, because values are changing everywhere. So the slope will be highest here because the current is highest here, and slope will be least here because the value is least. But this will be a quadratic kind of voltage. This will not go in flat. This flat option will not come. It will only stop. So if you draw parabola, you are picking up a section of this. Let's say from here to here, or other way, say from here to here. And because this is negative, so you have to go like this. It is dropping. So that is how this will come. And then again, the discharge cycle will continue. Clear? This is how the voltage capacitor will look like. Although I am drawing little bit exaggerated, this will not be so big as it is seen, but similar fashion it will be varying. You understand the point?
Yes, sir.
So now will you be able to draw the voltage and current waveforms properly? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
And what about people who are sitting with camera off? Any yes or no from your side? Quickly. We have a lot of things to cover in this class. So including me, only 11 have turned on, whereas 16 are there in the class. So what about remaining 5? Are you there or you have just turned on the camera? Deepak, I can understand you have internet issue. What about
Yes,
others?
sir. I also have the limited internet facility. That's
Okay,
why
try
I'm
to
turning on the
improve
camera.
it because this cannot go like this, right? So both of you,
Yeah,
Deepak and
sure, sir.
no, Madhvi, both of you try to have that. Who else is having internet problem?
Sir,
Manvin,
me.
your camera is not working, but you need to replace that or use some attachment in that. No, this needs to be little bit interactive, right? Otherwise, this one-way story will not help. This is fine. Now you are familiar with the boost converter properly. Is that fine?
Yes, sir.
Yes, sir.
Yes, sir.
Good. So let us move to the next class of converters. So far we have seen that we are having only one stage of power conversion. Let's say voltage source to current source, or we had current source to voltage source. So this we have seen is basically the buck converter, and this we have seen basically the boost converter. Now when we are dealing with DC-DC converter, we have some voltage input VG, some interface, and we have some output VO. What are the possibilities for VO and VG? There are only two possibilities, that either our VO can be less than VG or VO can be greater than VG. Is there any third possibility? So let me put equal to also, so that we include this thing as well. So now is there any third possibility for the DC voltage output? Can we have? See, either it can be more than this or it can be less than this.
Yes.
At the most you can keep equal. Is there any third possibility for this?
No, sir.
Correct? So whatever we see up to this point, this is all the basic what we can do for any DC-DC converter. Anything whatever we do other than these two operations is basically combination of this happening. You understand my point? So we may have buck boost converter. So what this would say that yes, we have some voltage VO which can be either greater than the input or it can be less than input. Having both the things included in the same, but it is basically we are combining these two converters together, nothing else. So which means what? That instead of this was single power conversion stage, single stage for power conversion. Now what we may have, let's say double stage power conversion. Is my voice clear to all of you?
Yes.
Yes, sir.
Yes, sir.
So basically buck boost converter what we may have, because we are starting with buck, so definitely it is starting with some voltage source. So let me just write the stages of this and then you will be able to appreciate what is happening. We have a voltage source which might be feeding through some interface a current source, and then this in turn might be feeding the voltage source again. You understand this point? So we have basically two stages of power conversion. In one stage what we are having voltage source to current source power flow, and then we have current source to voltage source power flow. Any problem in that? We can do, right?
Yes, sir.
Correct? So this is what basically when you see our buck boost converter or flyback converter, what we see generally this is what it is. We have a voltage source, we have another voltage source or voltage stiff element over here, we connect a current stiff element over here, obviously because the current stiff element can come only with the pole of the circuit, so we have these two, throw 1, throw 2. Do you recognize this as the common buck boost converter?
Yes, sir.
Yes. Yes,
Fine,
sir.
right? Any problem in this? So anything whatever we do is ultimately going to be some form of this power conversion. We may also have something like current source to voltage source and then voltage source to current source. This kind of arrangement as well. There is no problem in that. That we may call as boost buck. Because we know whenever we go from voltage source to current source, it is basically buck operation. Whenever we go from current source to voltage source, this is boost operation. So similarly here, from current source to voltage source, we have boost and then we have buck. You understand the point? This is how you can visualize any general converter, DC-DC converter, in terms of how the power is flowing between the two sources. Is that clear? So definitely
Yes, sir.
there would be some assignment questions, some examination questions based on this kind of arrangement. So be prepared. Now you can draw how the inductor current is going, how the inductor voltage is there, and then how capacitor current and capacitor voltage is there. All these things you can draw. Basically, again, you may have two configurations. One, when you connect to PT1, it is basically this. And when you connect to PT2, it is basically this. So you can say T on for PT1 and T off for PT2. So during T on and T off, we have defined the circuit. Now you know what voltage is applied across the inductor during these intervals. So you can draw that current, and based on that, what current is flowing into the load, and then based on that, what is flowing into the capacitor. And then you can draw the voltage profile of this capacitor. Is that clear? Any problem in that?
No, sir.
Now we will move to the another important aspect of this power converter. So far, we have only used this single pole double through switch for realizing everything. This is what we have used, right? Anywhere you can write T1, T2 based on how your circuit is operating. Now, how to realize this switch? Because unless we do that, we cannot make the converter. Theoretically, we have done all the things, but how to make this switch? So here what we have to understand basically that what we are trying to do in this, when we are connecting a single pole double through switch, what we are basically trying to do. Now, let's say there are two states for this switch. First state when PT1 is connected. So now when P is connected to T1, this is one configuration in which the switch can be. The other configuration is when the switch can be connected to PT2 configuration. Correct? These are only two possibilities. Now what will happen basically when we have these two possibilities? See from the current flow and voltage blocking point of view. Ultimately, that is what we want. We want it to have some current flow and block some voltage. Is it not? Now, when it is connected to PT1, what basically this is doing? This is conducting a current from P to T1 because here we have current stiff elements. So that's why direction will be this. Correct? Direction will be dictated by this current stiff element. So basically between P and T1 we have current flow when it is connected to T1, and between P and T2 again the polarity may be different. So say some polarity of voltage blocking between these two. You understand the point? Now when we have PT2 connection, again the current is flowing like this, whereas we are blocking a voltage like this. Polarity may be little different based on the circuit, but this is what ultimately we are doing. We are blocking some voltage between PT1 and there is some current flowing between P and T2. Correct? Now this can be realized by something what we call as switch, but here I am talking about ideal switch. What is definition of ideal switch? This each PT1, PT2 what I have drawn is basically an ideal switch. There may be, yes Sukumar,
Yes, sir.
any questions?
No, sir.
Okay. So for this ideal switch, again, when we say a switch, this is basically this. It may have a terminal. When you turn it off, that is not connected, and when you turn it on, it is connected. This is an ideal switch. These are two states for it, isn't it? So basically SPDT switch here is having two such switches connected together. Two ideal switches connected over here. Now, what are the properties of this ideal switch when we talk about? So obviously this is called open state or off state. And this is closed state or on state. There are only two states possible for any switch, right? Now, when we say that voltage is off, what we are trying to say basically is that there is no current flowing through the switch. The current conduction is zero, and whatever voltage we want, we can block. It can block any voltage across this and any polarity. It can block this polarity as well as this polarity. Understanding my point? This is the off state of the switch. In the on state, what we have basically, we have any amount of current flowing through the switch. And so let me classify this as I off and I on. So I on is basically not zero. It could be anything and any direction. Whereas the voltage across the switch when it is on, you call it V on, is equal to zero. There is no voltage drop across this. Do you understand this?
Yes, sir.
Sir.
Now tell me, what is the power loss when the switch is off?
0.
Zero. So during the off time we have zero power loss, and during the on time?
Sir, 0.
Zero. This is the property of the ideal switch. Whenever it is open, it will not allow any current across it. It will block any voltage. So ideally VB is tending to infinity and any polarity. Similarly, in the on state, we have I on, which is not zero. So ideally it can go to infinity and any direction. Whereas the V on, the voltage drop across the switch during the on state is zero. So hence what we are having that in both these states we have zero power loss. And another characteristic of ideal switch is that going from one state to another state is instantaneous. The time taken for this transition is zero. Correct? The energy involved for this transition is also zero. These are the ideal characteristics of this switch, or these are the characteristics of ideal switch. There is no time involved for transition. There is no energy involved for transition. You understand my point? Is that clear?
Yes, sir.
Yes, sir.
Now,
Yes, sir.
if we have to draw, because everything we understand from voltage current characteristic. So if we have to draw the IB characteristic of this switch, what basically we are having ideally, it can conduct any current, positive as well as negative. And it can block any voltage, either positive or negative. So this is basically operating in all four quadrants. These are the four quadrants what we talk about. Current may be positive, voltage may be positive, or voltage may go negative while current is positive, both negative, both say voltage positive and current negative. These are the four quadrants, possible operations of any switch. An ideal switch operates in all four quadrants. So which means this can be applied to any circuit without any thought. It can block any voltage, it can conduct any current. Is that fine? You understood the properties of ideal switch?
Yes, sir.
PI characteristic?
Yes, sir.
However, we don't have ideal switches in practice. So we have some real switch. Now what could be the real switch? Can you name some?
Diode, transistors.
Okay.
BJT, MOSFET,
Diode, then
BJT,
Transistors.
MOSFET,
BJT, MOSFET,
IGBT,
IGBT, and so
GTO.
on. Okay, several may be there. Now, if I ask you, how do you decide which device can be connected to which place? How do you decide that?
IV characteristics.
Yes. So we need to see the IV characteristic of each device, what it has, and based on that, it can be applied to a particular circuit or a particular place based on the requirement. You understand my point? So let us say we have diode. First switch we take as diode. Simple PN junction diode we have, and of course there is no control terminal for this. So this is basically an uncontrolled switch. And we know that if it is forward biased, it will conduct the current. That's all we know, right? And if you apply a negative voltage, it will block the current. You understand the point? This is the property of diode. Now, if we take the current direction as the positive way of conduction or positive direction, the current flow, then the IV characteristic can be drawn. First, we draw the ideal IV characteristic. Then we go to the actual one. So we have current on this axis and voltage on this axis. So what we have, current is positive. Correct? And we have voltage, what it can block is negative. Ideally, any voltage it can block on the reverse direction. So please understand, when it is forward biased, ideally there is no voltage across this, it is zero. That's why the characteristic is not extending on this side, ideally. Whereas for the negative side, there is no current, so it is not extending on this side. This is the ideal characteristic for the diode. So what we say, whenever there is current conduction, we say that diode is on. And whenever it is blocking some voltage, we say that diode is off. So these are the two states. Now, obviously, when we say that practical diode, what we will have, so basically, it will not immediately conduct. It will conduct only after the threshold voltage is crossed. Okay, and it will continue. So obviously not up to the infinite value, but somewhere it will stop. So this is some amount of voltage we need to inject for this diode to break the barrier, that PN junction barrier. Okay, this is nearly equal to say 0.7 volts or something. Before that, this does not conduct actually. And when we are applying a negative voltage, so there is some breakdown voltage associated with this. It cannot block infinite voltage. After a certain voltage, the junction will break down and it will conduct and it may get damaged as well. Understanding my point? This is the first switch, what we are talking about. So this is the ideal characteristic, what is drawn in red, and the black one shows the real characteristic or the practical characteristic, what we see. Now, when it is conducting, when it is in on state, so basically it is operating in which quadrant? In the second quadrant. The current is positive, whereas voltage is negative. Understanding my point? Now when it is going on, how this will be represented in the circuit is basically like this. There is some slope for this characteristic, and that corresponds to some, say, R on, and then some voltage you may call as on state voltage. This is the equivalent circuit for diode when this is on. So if the current is flowing, basically this amount of voltage will be against the current direction. So there is some power loss associated with the diode when it is conducting. And what is that power loss? Say I current is flowing, so obviously I square R on plus V on into I. This is the power loss associated with the diode when it is on. Correct? This clear to all of you?
Yes, sir.
Okay. For the off state, what we have basically that more or less diode behaves like open circuit. There will be some leakage current, but that is very small. So as long as this breakdown voltage is not achieved or this is not applied, we have power off nearly equal to 0. So this is called conduction loss. And this is called blocking or off state loss. So this can be regarded as 0 in most of the cases, whereas this is basically a finite number which we need to have in our computations. Clear? You understood about diode, how it is behaving? Okay.
Yes, sir. Yes, sir.
Next device what we can take is basically BJT. Now you all know that BJT has basically 3 terminals: collector, emitter and base. And based on this base current, it is controlled. So this is kind of controlled switch. Fine. So here I stop, and I would suggest that you go and revise all the things related to BJT, MOSFET, IGBT, whatever you have studied earlier. We will discuss this part and complete the realization of the circuit. And also we will move towards the control aspect of the motor drive. So first we will try to have DC motor control. So then revise some of the control lectures also what you might have attended. Fine. Any doubts in this so far?
No, sir.